Hi there. In this video, we're going to do a hypothesis test, and we're going to do it with simulation and also a tactile simulation using some kind of either cards. I'll show you about that, or you could use coins as well. And then we're going to use a computer simulation after that. Okay, so let's look at the situation. So this was reported in the Washington Post, so you can read more about this, follow this link. There's a woman named Joy, and she and her husband lived in the UK, and Joy smelled a subtle musky odor on her husband. His name was Les, and she hadn't noticed that smell before, okay? So, and at first she thought, oh, maybe it's just the sweat, his sweat. He works as an anesthesiologist, so he works long hours as an anesthesiologist. Then it turns out he was diagnosed with Parkinson's disease about 6 years later, okay? So at that time, she suspected the odor might be a result of the disease. Okay, so she, of course, contacted some folks about this. Scientists were very interested in this. They were intrigued by her claim, and they designed an experiment. Okay, so we're going to do an experiment here. Or kind of simulate this experiment to test her ability to smell Parkinson's disease, okay? So Joy was given 12 different shirts, okay, and each was worn by a different person. 6 of those people had Parkinson's disease, and 6 of them did not. Okay, so the shirts were given to her in a random order, and she had to smell each shirt and decide whether each shirt was worn by a Parkinson's patient or not, okay? So let's think about what kind of variable is this? What are we measuring, right? What were the scientists measuring here? They had to decide, or they had to record. The variable is the piece of information we record, right? So was Joy giving them a number? No, it wasn't numerical, right? It was a yes or no. It was a categorical. It was, did this person, by smelling the shirt, does this person have Parkinson's disease or not? Okay, so this is a categorical variable. Okay, it's a yes or no. It's, does the person, does the person have Parkinson's or not? But you also might be thinking, well, did she get it right or wrong? Okay, so there's kind of 2 different things going on here. They would record Parkinson's or not, and then also, did she get the answer right or wrong? So Parkinson's or no, and then right, sorry, not with a W, right or wrong. Okay. Okay, so let's write out the hypotheses for this test. So we have our null hypothesis, H naught. We always write H sub 0 with a colon, H naught. Okay, so let's think about this. It's a proportion, so I'm going to write P equals, it's categorical as a proportion. So if Joy is, we're going to assume, like our null is the null is no effect, right? So we're going to assume, what if she cannot tell the difference at all, okay? In that case, she would be randomly guessing, and so that would be like flipping a coin, okay? So that would be a 50-50. So the null is, Joy is guessing randomly. Right, so the null is just no effect. The alternate, or HA, is the thing we're trying to show, or thing we're trying to gather evidence for. Okay, so in that case, if she really could tell the difference, we would expect her to get more correct, right? Fewer correct would not be evidence of telling the difference. It would have to be more, and right, significantly more. So P greater than 0.5, we would say that she can identify Parkinson's at a rate greater than chance, right? And that's what it means to be statistically significant. So Joy can identify Parkinson's. Okay, so a couple other things just in the way of review. This is a greater than, so this is a right tail test. We're going to be going to the right. Okay, and then we want to see if the result is statistically significant, right? So if she can get more than 50% right, significantly more. So we'll talk about what that means. Okay, so in this video, we're going to do a physical simulation. We'll do this a couple times through the term. It will be really helpful if you have 12 of something. Okay, so you can pause and get this. Either what I have are 12 cards, and half are red and half are black. They don't have to be the same suit 1 through 6. I just did that for ease. So you could have 12 coins, or you could have 1 coin and flip it 12 times. In class, if you're doing this physically in class with me, you'll see some shirt cards like that. So I'm going to do one with this to help you get the context of how this works, and then I'll do some with the cards as well. Okay? Okay, so if you need to pause the video and get some cards or coins, go ahead and do that. Okay, so what we're going to do is, to do a simulation, we are always simulating the null distribution, right? So we assume the null is true. That's how we do a hypothesis test. So we assume the null is true. And what we do is we build a null distribution. What is likely under the null? Okay, so I'm going to write assume the null is true. And in this case, our null is that Joy is guessing randomly. Okay, so in this case, so she's guessing randomly, and we have a sample size of 12. Okay, so you will need 12 cards, or if you're doing this in a class, you'll have 12. Your group will have 12 cards. Okay, so the way it's going to work is you're going to mix up the cards, and then we're going to randomly divide them into 2. So we know that 6, and I don't know if Joy knew this or not, that 6 people had Parkinson's and 6 people did not. So let me show you what these cards look like. There's a shirt, and they're just a blank on one side because she wouldn't know. But then the researchers would know, right, that some people had or did not have. So these say no. Where's one? Yeah. So here's one where the person did have Parkinson's, and this is one where they did not. So I have 6 of each in this deck of cards. And then what I'm going to do is shuffle the cards so they're all mixed up, right, because they would have given the shirts to Joy in a random order. Don't want any patterns. Whoops, I'm going to lose my cards. Don't want any patterns going on. Okay, even better if you use a random number generator. Okay, and then I am going to just deal them out in 6 in each pile. Okay. Okay, now let me set this one aside for a moment. Okay, so we're going to say that these, and again, this is the null, but we're going to say, so this is the group that she identified as having Parkinson's. Okay, so I'm going to get my next page out here, which is where I'm going to record, and then the other deck I'm going to say are the ones that did not. Okay, so in my tally sheet on the next page here, I'm going to write a tally mark for each one that was correct, okay? And I have to do this for both groups, okay? So this is the has Parkinson's. So there's 1, that one's not right. Has Parkinson's, that one's not right. That one's not right. Has Parkinson's. Okay, so there's 3 right in this group. You could do a tally mark, or you could just write 3. And then this, I'm going over here. The correct answer would be does not have Parkinson's. So that one's not right. That one's right. You can probably see it's going to be 3 again, right? Because if 3 were right in the first 1, then 3 have to be right in the second group. Yes, okay, so 3 right there as well. 1, 2, 3. Okay, so that is 6 correct, and we're going to get a proportion for that, so that is 6 out of 12, which is 0.5 or 50%. Now, this is because we're doing the null, right? With what's likely under the null. Now, will it always be 6 and 6? Probably not, but we want to do a bunch of these to see, right? A bunch of these trials. That's just one. Okay, now let me do it with cards on the next one. And you're going to do 3 of these as well, and we're going to mark them on a graph. Okay, so these are the cards I have. I have 6 red and 6 black cards. Okay, so let me show you that. So it's a little magic trick here. Shuffle them up, or you could also flip a coin and do it that way. Okay, if this is an online class, then each person's going to do 3 and put your results into a survey so we can get the whole class. Okay. Okay, so again, I'm going to deal this out, 6 on the left and 6 on the right. Okay, set this group aside for a moment. So, and I'm going to say that red would be a positive. Red has Parkinson's, okay, just because we have to define it one way or the other. To me, it's easier to remember if red has Parkinson's. So that means I'm looking for red to be correct here, okay? And I actually have 3 reds. Okay. And then for does not have Parkinson's, I would be looking for the black ones. And of course, it has to be, if it's 3 on one side, it has to be 3 on the other. Okay, so I got 50-50 again. Okay, let me do it with the cards one more time. Okay, deal them out evenly to each side. Okay, okay, this time I got 4 red that do have Parkinson's, so that would be correctly identified. So I got 4. And then does not have Parkinson's is black, and so there are 4 black ones as well. Okay, good. I'm glad I got something different. So that's 8 correct. 8 out of 12. Let's see, I don't have that one in my head. Where did I put my calculator? I think it's probably 3/4, but let's do 8 out of 12. Oh, 2/3. Yeah, if we reduce that, it's 2/3. So 0.6667. Okay, great. So we've got our 3 trials. And so I'm going to remove this page. Okay, now when simulating the null, we want to see the shape of this distribution. So we want to do many trials, okay? But I think it's reasonable for each person to do 3. So we have this by proportion correct in samples of 12 when guessing randomly, right? So that's the null. So this is a distribution of the null hypothesis. We could do counts, that's another way to do it, but we're going to focus more on proportion. So 50%, I'm going to put a dot right there, and then another dot, so I'm going to put that right on top. So this is called a dot plot. And then 8 out of 12 is 2/3 or 0.6667, so that would be 6 and about 2/3 of the way over to 7. Okay, great. So if you're doing this in, if we're in a class, then we made the rest of the class. You can see that distribution. If you're doing this in an online class, then look for the link with a form to put your your 3 trials in, and then you should be able to see a spreadsheet of the whole class's trials. So you can get a little, make a little graph of those, okay? So you can see what the shape looks like. Now, that said, it would take a really long time to, we want to do a lot of repetitions. So we're going to move from a tactile simulation to a computer simulation. Okay, and most of the time we'll just do the computer simulation, but I think it's really good to do this one physically to get a sense of what the computer is doing. Okay, so, and it will take, it will be much faster on the computer. So I'm going to show you an app called StatKey. Okay, so you should have a link to StatKey, and then this is the randomization test for a proportion. Okay. So, okay, so we're going to enter some other stuff that we need here. Let's set it up a little bit first. So our null hypothesis, there's a place to enter that here. We are going to use the default, so I didn't need to click on that actually, but we're going to use the default of 0.5. And then in order to, for the computer to simulate this, it needs to know our sample size. So we actually have to put in our sample proportion. And so I'm going to tell you that, I'm going to go back to the notes for a second. I'm going to tell you that in this experiment, Joy guessed 11 out of the 12 shirts correctly. Okay, is that surprising? So that's the result. And from this, we can write our observed statistic. So this word observed statistic or sample statistic mean the same thing. Those are general terms. In this case, we have a proportion, so it'll be a sample proportion or p hat. So in this case, we have a sample proportion. And our p hat is 11 out of 12. And let's get a decimal, or I think StatKey will calculate that for us as well. 11 out of 12 is 0.9167. So you can see I'm using 4 digits for everything. And also I could write approximately equal there as well. Okay, so now we can go back to our simulation. Let me find it. We need to put in, let me go back and show you. I clicked on Edit Data, and now I can type in 11 out of 12. And you can click or you can hit Tab to get to the next one. Okay, great. So in our original sample will always be that one sample we entered. So you can see 917. StatKey only uses 3 digits, so they rounded it to 917. Okay, so now we can do our simulations. Let's do one. So click on Generate One Sample, and that is like one trial with the cards. Okay. Then this second table down here on the right shows you the result of that one sample. So this is like the last one I got, which was 8 out of 12 correct, 0.667. Okay, and there's a dot at the bottom. Okay, so this is just like the dot plot we were making. Let me generate another one. Okay, this one, she got, well, it was simulated under the null. If we were just guessing, they got 7 right. Okay, and that's 0.583, so put that there. So let's do a few of these. 6 out of 12, 50-50. 7 out of 12. We could also get fewer, right? So there's one. There's 5 out of 12 correct. Okay, so you could also do this with, you could see how you could also do this with a coin flip as well. And we could just flip coins over and over again with a 50-50 chance that would be another way to simulate this situation. Randomly guessing is like a 50-50 guess. Okay, so just do a bunch of those. What we're interested in is what does the shape of this look like? Okay, I just did a bunch of ones. Now I can go up to 1,000. In general, we'll do about 2,000 repetitions, okay? Okay, So this is what's likely under the null, and you may have been anticipating this shape, that it's roughly symmetric, bell-shaped, like a normal distribution, okay? So if certain conditions are met, we can use a normal theoretical model. Here we're going to use a simulation. Okay, so this is our null model, and what we want to know is, well, that 11 out of 12, 0.917, how likely is that under the null? And that is the p-value, okay? So I'm going to click on right tail, because this is a right tail test. When I click on any of these and the boxes come up, these are the default values, so I always need to edit these boxes. The number on the bottom is the number along this number line. So in this case, it's the percentage, the proportion correct. And then this is the box at the top is the proportion out of all the simulations. So if we took this number, the number of these like red X's for each dot, divided it by 2,000, we would get this number. Okay, so I need to edit the box at the bottom, and I need to put 0.917. That's our observed statistic, our sample proportion. And we can see that is extremely unlikely under the null, right? There were no simulations where we got 11 out of 12 just by guessing randomly, right? Or flipping randomly. So it seems pretty obvious that something is going on here, right? Which I'm sure when you saw 11 out of 12, you instantly thought that, right? Oh, wow, she can really tell. That is statistically significant, right? So remember, a small is significant. This is our p-value. It's the chance of getting the null, it's the chance of getting what we observed, or towards the tail, because anything away from the null is also evidence against the null. So you can see the null in the middle here. Okay, so our p-value is 0, so that is very unlikely. Okay, so let's go back to the paper, and you'll also be doing a lot of screenshots. So when you do a simulation for a homework problem or a quiz or anything like that, you'll be doing a screenshot and including that as part of your work. Okay, so back to the notes here. This explains what we just did. So in StatKey, we did edit data and we entered 11 out of 12. And the null the default is 0.5, but often you have to change the null. So we generated one sample a bunch of times, then we generated 2,000 samples. Okay, let me get the next page here. Okay, now often I'll have screenshots so that you have that in your notes to remember what we did. So this is the randomization. This is a screenshot of a very same setup of the simulation. And so we did edit data, and then often you have to change the null, but this one was the default value. Okay, so when you do edit data, you enter p hat. Okay, and then here, this is enter the null value. Okay, and then in original sample, this is our p hat. So you always want to check your p hat right there. That is your p hat. Okay, and then we also selected right tail because this is a right tail test. And then we put our p hat, we need to enter this down at the bottom. It could be, if it's a left tail test, it could be on the left. We need to enter it right here. And then this is p hat, and then this is our p value. Okay. And these can vary, right? So each simulation will be a little bit different. So if you did yours and you got 001 or 002, that's totally fine. Simulations will vary, and that's why I have you upload a screenshot. Okay, and then to really understand what this graph is doing, this is the proportion of correct guesses out of 12 tries. Okay, and that's under the null So I could say when guessing randomly. Okay, because it's the null distribution. Okay. Okay, so now let's take our results, and then I will often take the results from the screenshot simulation if it's different, just so that your notes match what you're seeing in the screenshot. So write the p-value from your simulation. Okay, so I'm going to write the p-value equals 0, right? Getting 11 out of 12 never came up in any of the simulations. But remember, you will have, these will vary, okay? These vary each time you do a simulation. And so if you're doing a simulation for a MyOpenMath homework question, that's taken into account, that your answers will vary a little bit here and there. And they're coded to allow that variation, okay? If your answer is not accepted, there's a couple things you can do. One thing is you can just rerun the simulation. It just takes a couple clicks. And that's because maybe you just got a very unusual simulation. Another thing you can do is email me or post to the forum with your screenshot, and then I can see, oh, that is correct. I'll expand the tolerance a little bit, okay? There's a balance because I want to make sure you're doing it correctly, but I also want to allow for that variation, okay? Okay, so you'll run into that in this class. Okay, so that is our p-value from this simulation. What does the p-value represent? Let's review that, okay? The p-value is the chance, it's a probability, the chance of getting the observed result. Or towards the tail. Or you may have heard or more extreme. So we're always going out toward the tails. Under the null hypothesis. Okay. And then, after we get our p-value, we compare it with the significance level. Then we compare the p-value with the significance level. Oops, let me move my paper up. Okay, and the default is 0.05, okay? So sometimes you'll be given a significance level. If you're not given one, then we'll use 0.05. 0.05 is the default. Okay. Okay, so now we can write out our conclusion to review that part of the hypothesis test. Okay, so first we're going to state our p-value with a p-value of 0. Then we either fail to reject or we reject the null, okay? So small is significant, right? Let me write that back. Write that up here. Small is significant. How small? That is the significance level. So because I should have written out somewhere here that, let me do it over here. 0 is less than 0.05, okay? Okay, so that means it is statistically significant. With a p-value of 0, we reject the null hypothesis. And then we talk about the evidence. We have evidence or we don't have evidence for the claim, okay? And with a p-value of 0, that's very strong evidence, right? We can also talk about the strength of the evidence. So in this case, we have very strong evidence that, and then we want to put in the context, that joy can identify Parkinson's disease by smell. Okay, with a p-value of 0, we reject the null hypothesis. We have very strong evidence that Joy can identify Parkinson's disease by smell. Okay, so I hope you've enjoyed this example and getting to sort of review hypothesis testing and using the method of simulation, which may be new or maybe not new to you. And this is a real study. So under this video, you'll find some links. And then another super interesting thing is that one that she got wrong, later that person was diagnosed with Parkinson's disease. So she actually got them all correct. Okay, so 12 out of 12, extremely unlikely under the null, right? So I hope you enjoyed that, and look for, there's a video and also article about that. Okay, great. I'll see you in the next video.